Thank you, Coca, and can I also thank the others on the organising committee for this meeting. It's been a great opportunity to return to Brazil after, I think, 5 years pre-COVID. I wanted to start today by saying that my plan today was really to talk about some work that we've been doing in the Australian Rivers Institute over the last probably 3 decades, really aimed at how do we apply our science to improve the health of our freshwater and indeed our coastal ecosystems, and in doing that also improve or diminish the threats to our own water security. And this has been some work that's been ongoing for some time in partnership with colleagues within the Institute and also colleagues within industry and in local and state government. I wanted to start by saying, and many of you know, that freshwater systems are ones that get hammered by a whole range of stresses, and they range from the obvious things of constructing reservoirs and fragmenting rivers, altering their flow regimes, and in the case of our development, isolating the river channel from its floodplain, particularly in agricultural land, but also in our cities. So our rivers become terribly fragmented and isolated, both longitudinally and laterally. And of course, there are a whole range of other stresses as well. Pollutants of various forms, they come in through point sources, of course, and through diffuse sources or non-point sources of pollution. And those pollutants, again, occur in a multitude of forms and have serious impacts on freshwater systems. And the pressures that we've exerted on our freshwater continue to grow. And these are some papers from some work we did under the Global Water System Project with Charlie Vorismati. Those pressures, whether it be water withdrawals or whether it be nitrogen or phosphorus pollution or the construction of dams, all of those trends are still going up as we speak. And some of the work that we recently did, the paper, the maps, if you look on the right-hand side of the screen there, are looking at projections that if we continue as business as usual with the predicted climate change and predicted global growth, population growth, what we're going to see is those stresses, the threats, broad set of threats to freshwater systems intensifying, and particularly intensifying in areas where the threats are already quite severe, places like you see there in Asia and India in particular. And of course, those sorts of threats have had already a tremendous impact on biodiversity. It's not just the really small things, small invertebrate animals, it's some of the larger and charismatic things that live in our river systems and live on our planet. And this represents a significant component of the global biodiversity. It's, in the order of 40% of the world's species of fish. About a third of the species of animals with backbones live in or are associated with freshwater systems. So Dave Tickner made the point very well yesterday that this is an incredible component of the world's biodiversity, which is under extreme threat. And as David put this figure up yesterday, when you actually look at the state of decline in freshwater populations have been really quite dramatic since the 1970s. And, there are things that we've recognised, and this particular paper discusses the number of things that we can do to actually bend that curve of biodiversity loss. And the ones that I wanted to focus on today are really around improving water quality and associated with that, protecting and restoring critical habitats. And that really is going to be the focus of my talk today. Now, particularly in our part of the world, diffuse pollution is really one of the major threats to our waterways. And it's a threat that we see all up and down the eastern coast of Australia, but it's, when you look at many countries in the world, diffuse pollution, non-point source pollution is really one of the major impacts to our waterways. And what we see, and this is showing a map of southeastern Queensland, the region that I want to talk about in particular at the moment. What we see increasingly is that every time we get an intense rainfall event, a lot of the material in our catchments runs off into the river networks, impacts on our water supplies, our water storages, and goes all the way down to the coastal zone and has a really significant impact to ecosystems, coastal ecosystems. And in the bottom end of this particular system is a Ramsar-listed wetland called Moreton Bay, home to a whole range of endangered and charismatic animals. And that's under severe threat from the sediment and nutrients that are being washed out with every rain event in our upper catchments. One of the things that's become increasingly clear is that this is not just an environmental problem, it's a major threat to our own livelihoods and a major threat to water security. And there are lots of course, local impacts that we see from these rain events, the erosion of channels and gullies in the landscape. We see quite expensive loss of valuable farmland in the irrigated areas in the upper catchment. So, tens of millions of dollars of valuable topsoil being washed away. We see hundreds of millions of dollars worth of damage done to roads and other critical infrastructure in the region, bridges and so on. But there are also ongoing costs, the increased costs of water treatment, because the water treatment plant for the city of Brisbane, for example, gets overwhelmed with sediment. And so during a rain event, the city can actually run out of water because the treatment plant can't keep up with the sediment load that's coming through. The water storages are slowly sedimenting up too, so there's a potential for a loss of water storage over time. We know that down in the bottom end of the river system, that with every flood event, the Port of Brisbane has to invest, again, tens of millions of dollars in dredging the river channel and dredging a shipping channel out into the bay. And so these are very significant economic costs. And then the bay itself, the commercial side of things, the bay has a commercial and a recreational fishery, which is worth several $100 million. And again, that's threatened by these particular problems. So key point I want to make here, and I think this is one that's becoming increasingly recognised, is that we don't have to just argue this from an environmental perspective. It has significant economic and social impacts as well. Now, we certainly understand what the underlying causes of that erosion are. When you look at these catchments, they're no longer resilient to extreme weather events. They've been extensively cleared since European settlement, and particularly clearing along the floodplains and the riparian zones. That was something that the early Europeans did when they arrived. And broader clearing in the catchments, hardening up of the catchments with cattle and other hoofed animals, has compounded the hydrologies as well. So what we see now is, with any rain event, much more flashier flows in the system in response to that rain, and the flows get concentrated in gullies and river channels that have lost all their riparian vegetation, so they're very vulnerable to erosion. We've understood that, and we've mapped and we know the extent of that throughout the entire region. We've also, over the last 2 or 3 decades, worked with community groups and government agencies to come up with tools or guidelines on how you would go about fixing that problem. So there's a whole range of things that we can do that include planting of riparian vegetation, putting in pylon fields to slow water movement on floodplains, revegetating vulnerable hill slopes, or changing fire management or grazing management on hill slopes, fixing up gullies. These are the sort of the dry eroding gully networks that occur in some of the catchments. And in some cases, even reconnecting some of the wetlands that have been cut off, or even going to the extent of recreating them. And all of those actions we know are really designed to slow the rate of water movement, slow the rate of flow, reduce erosion, and trap and transform nutrients and other pollutants. And as I mentioned, that these have been really well explained in guidelines working with various industries. So there are very practical guidelines on how you do these kinds of projects. We've also know that land use, or the target of restoration, really does need to be around the riparian corridor. And when we've looked at a long-term data set of river ecosystem health for the region, it's based on a whole range of biological and water quality metrics. We know that the best spatial predictor of ecosystem health for freshwater is the amount of vegetative cover you have in what we've called the hydrologically active areas in the landscape. And, that's effectively the riparian zone. And so protecting that riparian zone, of course, is really a key policy and a key management decision that you might make. And it's interesting flying over here, and when flying into Sao Paulo, you actually see in Brazil, you see a lot of evidence where riparian lands have been protected from the adjacent farmland to a far greater degree than we see in Australia. And we can use that information to model how much would you have to restore, so we can take those relationships between forest cover in the riparian zone and river ecosystem health score and actually predict for communities how much would you need to restore to get your report card score, your grade for freshwater ecosystem health in that region to improve. And what we found is you could actually get good ecosystem health for freshwater systems if you have about 80% of the area covered, and moderate scores with around 60% cover. And so individual local governments can actually see how much of the riparian areas do they need to restore to be able to recover and improve the river health. But one of the things that's really clear from the work that we've done, and this is some work from a colleague, John Olley, who's a geomorphologist that was working in our institute, is that most of the pollution, particularly the sediment and the associated nutrients with that, comes from a very small part of the channel network. And this is a really good example of one of the smaller catchments in the region. And those red areas that you see mapped there represent about 10% of the catchment area, but they're generating about 60% of the sediment load. And the yellow areas, another 10% of the catchment area, generating about another 20% of the load. So if you were going to shut down 80% of the sediment delivery and sediment and pollutant load from that catchment, you would target restoration in those areas. But what we see, and you probably can't detect it on those maps, there's a whole range of little yellow dots and little red lines which indicate where local communities have done restoration projects. And what we see often is that they do restoration projects in places where it's easy to get access. They know the people, it's cheap, they have to spend the money quickly. And so what you see is often millions of dollars being spent on restoration, addressing less than 1% of the problem. And so this has been a real challenge. We see this in many of the coastal catchments around. So even though there's really well-intended effort to fix and restore the problem, those investments are often really poorly targeted, and the benefits, the multiple benefits, are often not fully quantified. So recently we embarked on a fairly large project, and when I say we, there's a very large team within the Institute that's been responsible for this work, came up with a project to look at how we address that challenge. How do we know and choose what actions to take and where to do them? If you are going to do actions, how do you optimise that investment, particularly if you've got a fixed amount of money? How do you know you're going to get the best outcome for the least cost? How do you get people to agree on that, to reach consensus, particularly if they've all got different objectives? And how do you build confidence? And by that I mean, how do you build confidence in the farming community, because you're going onto their land and saying, let's change land use on your property in some way? But also you want to build confidence in the groups that are putting the money up, the philanthropic organisations or the industry partners who might be willing to spend tens of millions of dollars to actually fix the problem. So our project really was focused on developing a multi-objective investment tool, and that's really aimed at being able to quantify what the costs and benefits are, multiple benefits that we could get from these sorts of projects. And that includes not only improving water quality, but reducing flood impact, improving river health, even the sequestration of carbon as a side benefit as well. And we want to be able to capture the costs and the benefits of all of those things. And then combined with that, we worked with a group at a partner university in Brisbane which designed a visualisation interface. So our thought was that this was going to be a tool that could take what is really a complex set of spatial information and actually let people explore scenarios. So could look at different options and allow groups to sit around and discuss and reach a consensus and and hopefully help them build confidence. So that was certainly the intent of that. And those two components we've aimed to link together. Now, I wanted to just briefly mention the partners that have been involved in this, and I put this up very deliberately to show you that our partners in this and our funders of the work include a number of industry partners. Urban Utilities is the organisation that's responsible for the treatment of wastewater in Brisbane. So they have a significant interest in being able to control the amount of nitrogen they release into the ocean and into the lower river. And so they're quite interested in, can we actually get offsets for that rather than have to upgrade a treatment plant or build a new treatment plant, which is going to cost them several $100 million. Port of Brisbane, I've already mentioned, they're very interested because every year they know that they're digging out sediment that's been washed down from the upper catchment. They've made it quite clear they'd rather spend their money on stopping the sediment coming than having to dig it out at the bottom end. And SEQ Water is the main water supplier, the distributor of water for the region. So they manage all the reservoirs, so they're interested in making sure the reservoirs don't get over-sedimented. And they also manage the water treatment plant, which is very dependent on the water quality coming from upstream. We have partners from local and state government who have a vested interest in the broader societal and environmental benefits. And then one of our major funding partners was a philanthropic organisation, and we worked together with the local NGO, Healthy Land and Water, which are very keen on looking at very positive environmental outcomes. And at the bottom there, our research partners. So just to describe briefly the architecture of the tool we've developed is really about optimising on-ground investment. And we developed the tool for a very small catchment in the region. But the intent of it is that it's a tool that can be taken to any other catchment and with the right data sets reapplied and run in other scenarios elsewhere. And we've done that, in fact, in another catchment, tested it out in another catchment in the region as well. So just to, I guess, describe briefly what it consists of, our focus has been on nitrogen and dissolved and particulate forms and sediment reduction. The reason we've focused on nitrogen is because that is the main limiting nutrient for water quality within the coastal environment. It's a major co-limiting nutrient for the river system as well. But the tool could be modified to include other pollutants, and it's very easy to include other pollutants like phosphorus, for example. What the tool is aiming to do is estimate the benefits in terms of that nitrogen and sediment on 4 key ground actions. So riparian riverbank rehabilitation, hill slope revegetation, remediating gullies, reconnecting or creating wetlands. And again, the tool could be modified to include or substitute some of these actions for other green infrastructure, or indeed, if you wanted to add some grey infrastructure possibilities as well. And importantly, we've worked very closely with economists on this. So importantly in the modelling, it's the cost of those actions. And we include the implementation cost, which is the cost of actually doing the work, planting the trees, building fences, constructing things, but also the opportunity cost. And the opportunity cost is the loss of income that a landowner would incur if you change the land use from its current form. So it's taking what the current value of that land is and saying, well, if they lose that land, that gives us a representation of how much money we may have to pay someone as a compensation if you were to change land use on private land, for example. Now, when I say that there are economic benefits, this particular example has actually been undertaken in that catchment. This is one that was funded separately by the Port of Brisbane and the Urban Utility. They spent $3 million of their own money. They paid for a major restoration project. It was about 3 kilometres long. Significant earthworks. It was a place of major erosion during a flood event in 2011. And that particular project, as I said, there was a $3 million investment. The modelling suggests it'll sequester about 440 tonnes of carbon once the trees are all grown, but it'll prevent some 16,000 tonnes of sediment and a whole range of nitrogen that I can't read on my screen here when entering the river annually. And if you put a value on that, and the values are based on what governments are prepared to pay, what industry's prepared to pay as offsets, we're looking at about $5,000 a year based on a carbon price, but more significantly, about $1 million a year annual return if we're costing sediment at about $60 a tonne, and about $231,000 a year based on a nitrogen price. And so the water utility, urban water utilities, is able to get a nitrogen offset for that particular work and save them money at their water treatment plant, which offsets the cost of their investment. The other thing I should say about that is that if you were doing this just for a carbon project, you wouldn't generate enough money to even buy the trees and put them in the ground. So coming up with a value on things like nitrogen and sediment has been really quite important. So the first part of the tools is really assembling data sets. We take our study catchment, divide it up into a number of what's called planning units. These are tiny little sub-catchments. I think there are about 126 of those. And with each of those planning units, of course, we're going to do one of, any of 4 management actions. We upload existing data sets. Most of this information is publicly available on things like topography, soil, land use, whole raft of different land use metrics that we can put into that. The heart of the model, and I don't want to get into how this works because my understanding of the actual model itself is pretty limited, but the major part of the modelling output is really based around simulated annealing, and these models are really designed either to look at optimising a single management objective through single objective simulated annealing, or more frequently using multi-objective simulated annealing, which is really trying to identify what the useful trade-offs are if you've got several on and often competing objectives for that. So this is really the heart of the types of models, and there's quite a lot written about this particular modelling platform. It's based on the MarkSan spatial modelling programs, and it's been quite adapted for our hierarchical river networks. Coupled with the main modelling thing is another scenario generator, and we've put this in to allow stakeholder groups, and these could be investors or they could be local government or community groups, to actually create their own scenarios. Because the way the models run really depends on what the ultimate management objective is. And so we could run objectives which are trying to set a particular target for a pollutant load. So we could say, what are the trade-offs in cost, whether it be implementation, opportunity cost, if we want to halve the sediment production. Or we could run the models and instruct the models to run in a very different way and say, well, we've got $20 million, what's the best outcome we could get for nitrogen reduction with a $20 million investment? Or what's the trade-off between sediment and nitrogen if we have a fixed amount of money? And so it's really quite important that our investors and our stakeholders, community people, can actually decide up front how the models are going to run, because that really sets the way in which the modelling takes place. Now, I saw this example as a sort of, a cartoon of what we mean by doing that optimisation. This is a typical sign you might see at the motor garage when you go and get your car fixed. That there's, they offer 3 kinds of service, but you can only have 2 of these. It's cheap, good and fast, but you can only have good and cheap, fast and good, or cheap and fast. And when you think of that, that's an optimisation decision that you need to make. You're really doing a trade-off between what's the cost of the work, the speed at which you want it done, and the quality of the work that you're going to end up with. And as the sign says, you can have cheap and fast, cheap and good, fast and good, but you really can't get all 3. And so it's not just that there are those 3 points in that space, if you like. There's actually a space underneath that which represent a whole range of solutions that you could choose. So you could opt for something that's a little bit faster and not as expensive. You could, say, I'm prepared to have cheap. But what you don't want is something that's expensive, slow, and of poor quality. So that plane there does represent the optimal space in which you could choose to make decisions. And you could be close to the optimal. You can't get to the optimal that you're looking for. Or you could choose to trade off that. trade off one against the other. And really this is what these models are designed to do, allow you to trade between these competing sorts of objectives. Now, I don't want to go into the detail of this, and you won't be able to read it, but this is the kind of model output that we can generate. This is for a scenario for that catchment. Said, if we had $20 million, what's the best outcome we could achieve for sediment and nitrogen reduction? The plot that you see, the three-dimensional plot, has a whole range of dots on it. Each of those dots represents one of the possible optimal solutions, and for every one of those really corresponds to a map. And in those maps, it'll show you what kinds of management actions you would do in each of those scenarios. So the darker blue areas there would tell you that, in that particular scenario, you would do riparian restoration in some places, wetland reconstruction in some, gully protection in others. And for each of those, we can actually then look at what the combined benefits of that are. And so when you actually look at that, for 20 million, one of the things to note is that the implementation cost is the same for every scenario. The model has been told that the cost is 20 million, so the model runs with only a $20 million budget. So the things that are going to vary in this are the opportunity cost and the effectiveness in reducing sediment and nitrogen. And in fact, in this particular example, it's a fairly modest reduction in sediment and nitrogen, about a 12% reduction in some of the cheaper scenarios that you might look at, cheaper opportunity cost scenarios. And you think, well, 10% for $20 million, that doesn't sound like a lot. But, if you look at the value of that in terms of just nitrogen alone, the water utilities are currently paying in the order of about $120 a kilogram for nitrogen as an offset. That represents about a $5.7 million return if the water utility was able to pay for that or get that offset to their business. And so, $20 million investment, and you're able to get a $5+ million return on that every year, it's enough to overcome the implementation cost, and it's certainly enough to pay for the opportunity cost, which is, I think in this case, about $1 million a year that you'd be paying landowners as compensation. So even in a fairly modest scenario like that, we can see that we can achieve that sort of, cover the costs of that sort of investment. The way the tools have been designed, some of the recent work that Dave Hamilton's group have led, is that it enables us to actually explore that particular relationship in a lot more detail. So we could look at that set of possible scenarios and say, well, let's have a look at some cheaper options up here. These are the space on that graph where the opportunity costs are the lowest. And you can zoom in on those and start to, with this particular dashboard interface, start to slide up and down and say, well, if I move this one up and down, what are the other ones doing? And if I choose a particular scenario, what are the actual management actions and where are they going to be taking place? And so we can allow people to explore the data set in a much more finer way. And then our stakeholders then can actually say, well, look, we actually like this particular option. It sort of meets all of our requirements. We've also experimented with really ambitious scenarios. So this particular one, we've run the models this time saying, forget about the cost. Let's try and halve the amount of nitrogen, particulate nitrogen, coming out of the system. And again, there's a whole raft of possible solutions. And as you might imagine, if you're trying to halve the nitrogen load, all of the models are running assuming that 50% reduction is the target. So the models now are showing for every scenario a 50% reduction in nitrogen. Associated with nearly every scenario in this particular example is a really significant reduction in sediment as well, about a 60% reduction in sediment. So these are really considerable benefits in terms of improving water quality, but really, really expensive. I mean, the implementation cost for this particular set of scenarios ranges from about $100 million to $400 million. And so you think, well, that's an enormous cost to do. And the real trade-off here, when you actually look at the relationships of these things, the real trade-off is if you try and minimise the amount of dissolved nitrogen. So if the more you try and remove dissolved nitrogen in this scenario, the bigger the opportunity cost. And that's because that requires often building wetlands on productive agricultural land, and so it's going to come at a really high cost. But if you're just interested in nitrogen load, and that's certainly for coastal environments, that's what we're interested in, you could actually choose an option which is, at the cheaper end of that, at the sort of 100 million scale. But again, that in terms of an offset, at that particular offset price, it's worth about $30 plus million a year. So again, you're coming close to recovering the costs of the implementation and the recovery, the opportunity cost, over a very, very short period of time. One of the other things we can do with these models is actually look at all the scenarios and say, how many times does a particular management action turn up in every scenario? So what percentage of the scenarios does a management action turn up in those places? So you could generate heat maps like this that say, well, if we were going to do riverbank restoration, the really dark areas on this map are turning up in nearly every scenario. So these would be really no regrets places to put your money, because they're coming up, no matter what the scenario you chose, doing riparian restoration in those places is going to be really important. And similarly, there are a few places in this particular catchment where you can see, it's really important to fix gullies. A couple of places where you might look for opportunities for wetland reconstruction, because they're the places that the model's picking every time. And so it is possible to use the models to generate this kind of information as well, to allow investors to start, well, if we're going to start doing things, these are some places that we're not going to misinvest our money, if you like, because they're always going to turn up as being really, really quite important. Now, once we've done those scenarios, the idea of doing the scenarios and doing it with stakeholder groups is that they can run scenarios. If they don't like the output, they can come back and redefine the scenario, rerun the models again. They can spend time deliberating about what the choice of options are, and then, sit down and collectively decide, we're prepared that this scenario, or this small set of scenarios, are the ones we want to look at. Once we've done that, we can start to explore what the broader catchment scale benefits would be. And one of the things we've looked at with that is, if you implemented those things at catchment scale, what would be the benefit in terms of flood risk reduction? And to do that, a team from one of the consulting firms in Brisbane created a rain-on-grid hydraulic model for the catchment, and then reran one of the really big flood events which occurred in 2011. And the rain-on-grid modelling matched very closely the recorded flow data for the catchment, so we were quite confident that both the flood extent and the hydrology in the model was as good as it was going to get. And then what we've done is taken the catchment scenarios, the three that I've looked at there, the $20 million investment, the halving the nitrogen investment. We've looked at the high cost and the low cost of that, so two options for that, compared with a base case in the model. So basically what this is doing is saying, we assume that you've done all that restoration in the catchment. What impact would you have on flooding in that particular catchment? And what that shows, and as you might expect, the very modest investment, the $20 million investment, had almost no influence on the flooding of that scale. But the big investments, where we're really, really revegetating large extents of the riparian zone, doing some gully repair, doing things on the floodplain, both the high cost and the low cost options for that actually reduced the flood height in the township of Laidley down the bottom end, reduced the flood height by 10 centimetres, and it delayed the flood peak by about an hour. Now, again, that doesn't sound like very much, but if you live in a house and the water came up 5 centimetres above your floorboards, then 10 centimetres lower is actually a significant benefit for that. And we can actually, and we haven't done it yet, but we could actually quantify the economic cost of that if we rerun where the houses that were flooded in that particular flood event. The extra hour, of course, gives people an extra hour to get their belongings to safety or get out of the places and avoid the flooding, and that's a significant benefit in itself. And significantly here at the upstream parts, when you look at it, that mid-region of this catchment suffered tremendous erosion on some of the big agricultural properties, and one of the farms lost $50 million worth of soil from that event. And so those options there show that we could halve the velocity, halve the discharge across that section of the floodplain, and would have prevented quite a bit of that damage. And so again, significant flood impacts that we could quantify and look at what the economic benefit of that would be. And I mentioned, some of the other benefits we can explore for each of those scenarios. We could look at what the revenue would be if you calculated how many trees you're going to plant in riparian zones or on hill slopes. We can actually put a dollar value on that over a 25-year period. And so these are the numbers. For the $20 million scenario, over a 25-year period, you'd generate about $9 million worth of carbon credit. But the other scenarios are generating far more than that. And again, that's another economic return that could help pay for the costs of implementing and the opportunity costs. So again, quite significant economic benefits. And if we add that, of course, to the nitrogen sediment, if we could quantify the economic benefit of that, what we find, even in these expensive scenarios, is that these benefits, the economic benefits alone, usually are greater than the implementation cost and the opportunity cost. So it makes economic sense, if you like, to actually do this sort of stuff. And then if we wanted to, once we've got these, we could also do a whole range of other catchment scale benefits. We could recalculate what the improvements are likely to be in river health score. We could look at what the terrestrial biodiversity outcomes might be if you started replanting networks of trees throughout the catchment as well. And they're often non-economic benefits, but they're ones that are worth capturing as well. Now, finally then, the other part of this particular work was that our group at partners at Queensland University of Technology are really big on developing visualisation tools, different ways of presenting information to people. And they helped working on this to come up with a visualisation tool that would take the output from our scenarios, the spatial models, if you like, and then represent them in a virtual space and allow people to explore in as realistic as we could to be able to see what the landscape would look like. And as I mentioned before, the idea of this is to build confidence, to show people that if you did this at scale, this is what it would look like, and this is the kind of thing that you're going to be seeing. And it's very hard to get that if you're working on the ground and planting 5 trees on a riverbank. It's very hard for people to see what the big picture might be if you did this at scale. And so that was really the intent. And so the actual tools, and it's actually quite difficult to get a really good impression of it on a computer screen, but the tools allow you, with a VR headset if you really want to get into it, to fly around the catchment, select different planning units, look at which ones are generating the most nitrogen or the most sediment, and then if you click on those, you can actually go down and fly down into the catchment. And quite frankly, I get tremendously motion sick from doing this, so I'm not a big fan of putting it on. But you can come down and have a look. This is what it would look like in this section if you planted out all the riparian zones. The yellow lines along the river there mean that was an action in that planning unit. You can come up and look at the costs and benefits of that, get up in the air and have a look at what it looks like. That's what it looks like without all the restoration. So quite a bare landscape, highly degraded. And so you can start to turn on and turn off what the restoration and stuff would look like. You can actually select catchments based on their contributions to sediment and nitrogen. You can also select them on the basis of their opportunity cost or their implementation cost. And again, go to any part of the catchment, click in, fly in. And as I said, it is really quite spooky when you're flying because you look down and there's nothing underneath you as you're doing it, which is quite disturbing sometimes. And you can, like I said, look at the implementation costs. Here's another example of a riparian zone. So you could click on that, go down. That's what it'd look like from the air. And you can get right on the ground and walk around. And so a farmer could be on their property and look upstream and downstream and get an idea of what the catchment might look like if they agreed to do this kind of large-scale restoration. Okay, well, just to finish up then, I'd just like to say, I guess, addressing pollution is a key action that we've seen to bend the curve of freshwater biodiversity loss, also the threat to coastal ecosystems. And it also has important outcomes, of course, for our own water security. It's, in fact, one of the Sustainable Development Goal targets within SDG 6. And addressing pollution is, you know, both in its point source and diffuse source is a real challenge. The point source pollution, in my mind, is really not so much a science challenge or a community. That we usually have the technical capability to deal with point source pollution, and it really becomes an implementation and a compliance challenge more so than a scientific one. But the diffuse pollution is really, you know, often put in the too hard basket. It poses a really great challenge, often because although we understand causes of the problem and the effectiveness of what on-ground actions would do, it actually requires investment in green infrastructure rather than grey infrastructure, and that tends to put government agencies and particularly water resource agencies off. They're much more comfortable with concrete than trees. And particularly the other key issue with it is it's often done on private land, so it has to involve multiple stakeholder groups and a whole lot of negotiation between landowners, industry, government to be able to do that. So that's often why we always throw the diffuse pollution challenge in the too hard basket. The other thing we know is it really does require targeted investment and coordinated at that catchment scale. It's just simply not possible to fix everything in our catchments, and we don't need to. We need to identify where the problems are coming from and what's the best way, the optimal way to deal with it. And really the approach that we've taken is what's the best outcome or outcomes that you could get for the least cost. And I would argue that now we have these sorts of tools available. Technology is really available now to be able to quantify full costs and benefits of doing this sort of stuff and what the trade-offs are. So we're not actually constrained anymore by our technical capability to advise groups on how to do this or what the benefits are. So it's not really, to my mind, that big a science challenge anymore. But there's certainly lots of remaining challenges, and one of those is the level of understanding that communities have about key river and catchment processes. That it's often really their understanding is quite poor, and what we see, particularly on landowners, is that in response to a flood event, they'll often get out and do things which they think is going to help for the next flood, but often makes the problem worse. So they'll straighten river channels, they'll remove woody debris, they'll remove riparian vegetation and make the channel more efficient. What they're actually doing is making increasing the power of the stream the next time round because they've increased the slope, they've decreased the roughness. And so we think that these sorts of visualisation tools and other forms of communication are really going to be needed to convince landowners that doing what they're currently doing often is not the right thing, and these kinds of things are not going to flood their property or cause problems. They're going to have a big benefit to them. I sort of sounded fairly positive working with all these agencies and government agencies and industry that they're all really on board with this, and a lot of them really are on board and see the value of it. But frustratingly, we still don't see major adoption of this at the scale that we've been recommending. So we still have some really major institutional impediments to adoption. The whole approval process for offsets, even though technically you can, a farmer can get an offset or a water utility can get an offset for things like particularly nitrogen, there's no clear market for that. So no formal market has been established in the same way there is a carbon market. And to get approval for a project, a water utility has to get approval from the state Environmental Protection Agency and negotiate with the farmer for every single project. And we're hoping that these sort of catchment planning tools allow us to scale that up so that we remove that institutional hurdle to that approval process, and that's yet to happen. The other main institutional problem we have is the local versus regional scale priorities. We work a lot with local governments, community groups. There's broad agreement that yes, we should be thinking at the broader catchment or the regional scale, and we're all in this together. But the moment that it comes to say, well, we're going to spend all our money over here, then another council or another group will say, well, I'm not, you're not spending my money over there. We want to spend money in our backyard. And so we have, in the case of the city of Brisbane, which has got a lot of money to pay for all of this, very reluctant to spend their money upstream where all the problems are being generated. And that's another institutional thing that we have to overcome. The other, I put as a challenge, but I think it's also a really major opportunity, is that there's lots of other nature positive or, carbon positive or net zero investments that are currently going on around the landscape. And so when you look at these catchments, people are out there planting trees for habitat for wildlife. They're planting on farms to get a carbon benefit. And it's all been done in isolation to the water quality side of things. So there's an entire effort being done aimed at the terrestrial restoration. It's completely decoupled from the water quality and flood risk reduction opportunities there. And I see that as a real opportunity for the further development of this and the further, discussion, is how do we bring those two things together? How do we put our water management objectives back into the broader natural resource management? And on that, I'd like to finish, and I'd be very happy to take any questions if there are any. Thanks.